Right, so apparently my microphone was off yesterday, so I did a whole bunch of summaries and ended up no one actually being able to hear it. So I'm going to basically re-answer the questions that I got asked yesterday. First question was, if we have carbocation, if we form a carbocation, do we know if it's a methyl or a hydrogen shift? And then the answer to that question kind of go back to why we even have methyl and hydrogen shifts to begin with. And this goes back to trying to increase the stability of the carbocation that's formed. So let's say I have this compound. So I've got this 3 methyl 2 butanol pantomime. Oh yeah, I mean, but it didn't do people a lot of good, right? I got a lot of emails afterwards saying like, "Hey, the audio was like, oh, it was just me," and I don't know, this computer's starting to have issues. Anyway, do you have carbocation rearrangement, and if so, do you have hydrogen or methyl shift? And the reason we have these shifts is simply because we're trying to stabilize the carbocation. So when we form the carbocation by this acid catalyzed substitution, first thing we produce is a secondary carbocation. And we have a hydrogen and a methyl group which can shift. So the question is, do we get a hydrogen or methyl shift at all? And so what we do is we look at what happens if we shift the hydrogen or if we shift the CH3. So what we're going to do is we're just going to swap the plus and the hydrogen, and we get this. So this is a tertiary carbocation. We go from a less stable to a more stable carbocation, so we do get this hydride shift. What about the methyl shift? Well, if I do my methyl shift, I pretty much just get the same molecule rotated 180 degrees. So I've gone from a secondary to a secondary. There's no reason for this shift to occur. So you're going to get a hydrogen or methyl shift, excuse me, if doing such a shift will increase the carbocation stability. Now, that said, there are more types of shift that can happen other than hydrogen and methyl shifts. You can definitely get this thing like moving down the backbone of the chain. So if it goes from like a primary to a secondary or tertiary, it'll do it. The problem is like that second shift, that second hydride, second methyl shift, really hard to kind of drive. It's more of a kinetic limitation. If you went to high temperatures, you could make it happen, but just kinetically, it doesn't happen fast enough. The second, and it's something I don't like testing on, it's an interesting thing that will show up on some of the homeworks, but it is kind of like a little nuanced thing. I'm thinking it's my internet connection today because when I logged on, it was like struggling to even connect. So we can thank Spectrum for their wonderful internet connection this morning. Let's make sure. So the weird one that can happen is actually ring opening. So let's say we take this compound and we hit it with an acid and we go through this carbocation, and the first thing we're going to do is produce a primary carbocation. This is highly unstable, but it's an alcohol, it is a good leaving group. So what can happen here is actually this bond will shift and we'll end up producing a cyclohexane carbocation, so that takes us from a primary to a secondary. Again, I don't like testing on this. It's a cool thing to know, like it's kind of one of those like building on this hydride methyl shift. We can get any type of carbon-carbon-carbon hydrogen bond shifts. I just don't like to test on it because I think it's kind of more of a measure of creativity than it is an actual fundamental understanding of what's going on. If you understand why hydride methyl shifts happen, you can rationalize why this happens. Now, second question I got asked yesterday. Where are you? Synthesis questions. Bulky basis for elimination. Do we need to specify the solvent? And does it matter what solvent we pick if it's aprotic or protic? So your two best bases for elimination, at least at this level, your tert-butoxide and your isopropoxide. These are very good because they are very large. They can do substitution, but they much more prefer to do elimination. So what solvent do you put them in? And typically what we do in practice is we put them in their own solvent. So for tert-butoxide, we put in tert-butanol. To make this, you do what you do in the lab. You take tert-butanol and you add sodium to it, and you'll react away some of the tert-butoxide to form, or some of the tert-butyl alcohol to form this tert-butoxide. Same thing's true with the isopropanol. If we react that with sodium, we'll get isopropoxide, and we can drive this reaction. In general, though, you don't need to specify the solvents. And the reason you don't really need to specify the solvents is we're not looking for the most practical synthetic routes. So let's say you want to do this synthesis. You want to substitute the alcohol to give you the terminal chloride. Well, depending on the reaction, you don't really need to specify the solvent because the solvent's not going to really impact it. So if you do this through thionyl chloride, SOCl2, this will happen. You're going to have pyridine in there, but you don't need to really specify it because the solvent doesn't really play a role here other than to basically dissolve thionyl chloride in the alcohol. But let's say you want to do the same substitution, but in this case you want to work with NaCl. Well, in this case, you're going to want to work with something like diethyl ether or tetrahydrofuran because here we can go SN1 or SN2. Here we only do the SN2 regardless of the solvent. So if there's a chance that you can go SN1 or SN2, that's when you need to start specifying the solvent, and that's why that discussion board was posted, was so that you can see that for some of these it doesn't really matter what the reaction conditions are, they're always going to proceed the same way. The trade-off with thionyl chloride here is that it's a super water-sensitive compound, so you're going to have to do this air-free, water-free. But we're not worried about practical synthesis here. We're worried about you knowing how to run these types of reactions, like to know what the different reagents do. Organic 3 is someplace, you go on to get your chemistry degree, you'll take Organic 3, where you'll start worrying about the practical side, like, well, why would you run this under these conditions? This is a lot cheaper to run under than this, but with this you don't have to specify the solvent. All right, so then I got homework questions, and the questions were 50, 51, 54, 55, 65, 71, and 78. So question 50. Principal organic product formed from the reaction of methyl bromide with potassium ethoxide. Click the draw structure utility. So we got this reacting with this, and the question is, what is the product? So part of the reason why we have to teach SN1, SN2, E1, E2 is that they all kind of occur together. You just basically favor one over the bunch. And sometimes you really can get like purely SN1, SN2 reactions. But the thing is that your base here has nothing to eliminate. So in order to do elimination, you have to have two adjacent carbons, one containing a leaving group, one containing a hydrogen. So there's no way that this methyl bromide here can do an elimination reaction because there's nothing to eliminate from. So your only option here is SN1, SN2. And honestly, it doesn't matter which one this one goes through, simply because this is a primary and it's an achiral carbon. So for this one, you're going to get the oxygen attacking the methyl group and breaking the bromine bond, and this will give you methyl ethyl ether. So I saw this a lot with the homework problems I was going over, is generally what you're seeing with a lot of these problems is that this is your nucleophile. So if you go through the notes, it talks about nucleophilic substitution looking like this. So like RCl or R bromide, you have the attack on the R, you break the halogen bond, and you get XR plus your leaving group. These are all going to kind of follow that same approach. So the next question, I think 51 was the same way. Yeah, make sure I still got audio. Now I'm going to get paranoid about it. In this case, for problem 51, you still got the methyl bromide, so that's still here. But instead of having ethoxide, now you have an acetate. And I draw the circle in here. Take organic 2, we'll talk about why it's a circle. But it's the same idea. You have the benzoate in this case, the negative, the deprotonate carboxylic acid attacking the methyl group to break the bromide bond. It's still this exact same reaction down here, just slightly different products. But it's still the same overall reaction. 54. Same reaction, so you've got methoxide reacting with ethyl iodide. This will try to do elimination, but ethoxide is kind of one of those, like, it's a strong base, but it's not, it's small. So we're definitely going to have a attack on that carbon and breaking it. There will be, in this case, you'll form, I'm sorry, it's a methoxide. Again, you're going to form the methyl ethyl ether. You will get some side product of this ethylene, but this is going to be the major product here. It's just a substitution reaction. Question 55 I'm dropping. This was definitely not a question I would have picked. I'm guessing they updated their cheomy again. It was kind of a weird problem because there's actually two ways the nitrate ion can attack this complex. So if I did pick it, it was probably because I thought it was going to force you to pick between the SN1, SN2 pathways. So this is your structure of nitrate, and you've actually got two nucleophiles on, I'm sorry, nitrite. So you've actually got two nucleophiles on nitrite. 2, 4, 6, 8. So you can get attacked from the oxygen or you can attack from the nitrogen. I don't think this is a particularly fair question because it's asking about an alkyl nitrite versus a nitroalkane. Those, in my opinion, are a little kind of esoteric compounds for you to know as an Organic 1 student. 65. Okay, synthesis problem. What I really hate about the McGraw-Hill software, and there's a lot to hate here, but I really do hate this aspect of their homework questions, is they ask you synthesis questions with reaction arrows drawn backwards. And so they say you're trying to get this, this acetate complex. You got a methyl group out, and you got an acetate group out. And you would think the way this is written, this was the product. It's actually the other way. You're finishing with the acetate and you're starting with the trans alcohol. And I find that incredibly annoying that they draw it backwards. But anyway, I do like the synthesis problems here. I just don't like how they're presented. So part 1 is asking you, how would you go from some precursor to this? So how would you make this compound? And you're trying to do it in a single step. So not how would you do it in 2 steps, how would you do it in a single step? And kind of the problem on my end is that answer A is always the right answer on the instructor side. So every time I do this, it looks like I'm picking A. It's because it's just this way the software works. So I've got a couple of options here. Shouldn't say a couple. I have several options here. And this is one of the starting options. So off the bat, can you synthesize from that starting compound? There is actually, because I've been looking up reactions to like add to the Organic 2 curriculum, there is actually a reaction that will take you directly from that to that. So the thing to keep in mind with synthesis, it's contextual. So based off the skill sets you already have, what can you do? Not based off esoteric reactions that we haven't learned. Based off reactions that we have learned, what can you do? Can you directly, which of these can you take directly from here to this? So what we're trying to do is we're trying to add an acetate group to this. Well, there is no reaction that will do this. So in principle, you could do an addition, but that's not going to work. This is a possibility. We could get by an SN2 pathway, we could take our acetate ion, displace the bromine, and end up getting this complex. So this is a possibility. This is not. And, well, actually, this is a possibility too. We can do what's called an esterification reaction. So in principle, we could do esterification. We could run this under basic conditions, and this would attack this, and we would get elimination. But again, esterification is not something we talk about in this course. This is 252. So this is discounted on the simple grounds that you don't know what esterification is or how to run it. So we can't directly go from this to this. There's no way to get that type of elimination or get that type of substitution. So the question is, will O-tosylate do it? And this we know will do it because tosylates like to go through an SN2 pathway. So we could run the same reagent. We could take the acetate and displace the O-tosyl group and get this complex. So which one is better to work? Because there are two possibilities here that will work. The acetate displacing the bromide and the acetate displacing the O-tosylate. And this is the answer. So O-tosylate is pretty much always guaranteed to go through an SN2 pathway, which is what we want. This isn't necessarily going to go through an SN2 pathway. So because of that, we'd rather do this because this is a sure shot. That said, this isn't necessarily a wrong answer, nor is this if you know how to do esterification. But we're going to go with the O-tosylate because it's a very good leaving group. So if I select the O-tosylate, the next step says, okay, how do you go from the O-tosylate? What could you directly go from here to here? And the answer is yes, just use tosyl chloride. So I can ask you what the reactant is in front of it. Well, just our starting alcohol. So the next question will ask you after you've determined what the previous reagents are is how would you react them? So question 4, how would you go from here to here? Tosyl chloride and pyridine is the correct answer. Part 5, choose the appropriate reagent. It actually gives you a couple of options here that might work, though definitely the CH3COO potassium. You're going to need the ion, the acetate ion, to make this work. All right. '71. All right, the principal product of 1-bromopropane with sodium hydrogen sulfide. Sulfides, the SHs are surprisingly not very basic at all. H2S is actually a surprisingly good acid, and we'll talk about that, I think, in organic too, where we start getting through a little bit on sulfide chemistry. This is just a substitution reaction. So with this one, you definitely get the sulfide. Again, this is just kind of your X minus. It's going to attack your halogen in its center and displace the halogen to give us bromide as the leaving group. Now, where was the weird one? Assuming 78 was the weird one. Oh, actually, no, this was a good one. I think it was 55 I got really tripped up on because I couldn't figure out what they were asking for. Okay, so you're asked to synthesize this methyl tert butyl ether, and you're given 4 possibilities. So, oh good, it actually scrambled the answers this time. 2-bromoacetate, plus potassium sec-butoxide, you've got sec-butyl bromide and potassium acetate. Tert butyl bromide plus potassium methoxide. And then you've got tert butoxide plus methyl bromide. So off the bat, you should be able to pick out that 2 of these don't work. So this here and this here, you're not trying to make an ester. You're trying to make this ether. So off the bat, these won't work. I mean, the idea here is that these acetate groups can displace the, I'm sorry, your your nucleophile here can displace the bromine, but all these are going to result in an ester. So these two possibilities don't work. So you're left with these two. Do you do a methoxide with a terp bromide, or do you do a terp butoxide with a methyl bromide? Honestly, both of these are feasible ideas. The question is which one is more feasible. So the reason why I say they're both feasible, this methoxide is pretty small. If you do it with this, you can get some elimination, but a majority of what you're going to get is the substitution product, because the methoxide is a base, but it's not that great of a base. Now, with the terp butoxide, you can only get the substitution because there's no elimination that can go on with this methyl bromide. So both of these will generate this product, but the terp butoxide with the methyl bromide is the better choice. And the reason it's the better choice is that you're guaranteeing that you can't do an elimination reaction. There's nothing to eliminate off of methyl bromide, so you can only do the substitution pathway to get the ether. So that was it for the questions I got asked yesterday. It's a lot easier to answer them when you've seen them before. So I've got the chat up in case there are any questions. I see at least one of you is active. So again, feel free to ask questions, and yeah, I'm just going to turn off the camera for now. So you got a question. I had a question about the lab worksheet for separation through commitment. It asked for the mass of the filter paper plus crystals, but what I did in the lab was weigh them in a watch gas. Can I just worksheet? Yes. So that's just kind of a suggested worksheet based off of what it is. There's practicalities associated with those. So if you ever just scrape it onto a watch glass, or you zero out the scale and you don't need to like write down the mass of a beaker or something, that's perfectly fine. It's just kind of provide it there, as long as your answers make sense in the context of what you're doing. So if you say like, or you're on the sheet is like measured it directly off a watch glass, is like, okay, that's fine. Definitely there are realities in labs though. So the big picture is what needs to be there. You need to have the mass of the crystals because that's relevant to calculating your percent recovery. But you definitely don't have to worry about like exactly how you acquire those masses. You should be able to find it. So if you go under quizzes and assignments under lab worksheets, there should be a submission link for it. you shouldn't need to do a pKa calculation for this lab. You may have downloaded an older worksheet, but yeah, you shouldn't need to do a pKa calculation for these. So the old lab manual from about a couple years ago used to require the pKa calculations. That's why it shows up in old versions of that worksheet. I'm not a huge fan of pKa calculations because they can be a little misleading. The reason you would want to do that type of calculation is to determine if you've made the solution basic enough in order to extract out your desired acid component. But the thing is, like, it's not a static calculation. Making that type of calculation presupposes that you have an excess of base. But the whole reason you're working with the pKa is determined under what pH conditions you would want to run in order to extract the acid. So it's kind of a catch-22. You're doing that calculation to figure out how much base you need to extract your acid, but you need to know how much acid you're extracting to figure out, there's just a lot that goes in that calculation. So generally what we do is we just run an excess. So if high excess of base and a high to remove acid impurities and a whole high excess of base to remove base impurities. And then we just neutralize from there. So again, if you're seeing pKa calculations, they're not supposed to be in there. That's actually from the lab from a couple of years ago, where students were required to do a pKa calculation. But again, you can't really use those numbers to calculate what pH you would want to extract the base or extract the acid, because the acid is going to neutralize your base. It just basically tells you at what pH you expect most of the acid to be dissociated. You didn't put a piece of filter paper, you put a piece of litmus paper. So litmus paper turns colors. So let's say you have benzoic acid. And it's a reversible reaction. And so you have the acetate ion, benzoate ion, and you have H+. And when the pH equals the pKa, 50% of this base acid head is in the ionic form. So if you want to extract out this compound, you need to be at a pH above pH equals pKa. You need to be at a pH above this. But the thing is, that's kind of a misleading statement. What we really want to do is we want to drive it all here. We want to go to the product, and we do that by adding a base. So this is more of a Le Chatelier. So let's say you add a whole bunch of sodium hydroxide. Well, now you kind of complicated things, because your sodium hydroxide is going to create a certain amount of acetate. And these two are reacting each other way. So for all the sodium hydroxide you remove, you're going to need to, that's going to affect your pH. The more sodium hydroxide you remove, the more pH you meet. The more your pH is going to go back down. So really what you want to do is you want to add enough sodium hydroxide that you react away all the benzoic acid. But then what happens is that you get the reverse reaction. This is soluble in the ether. This is soluble in the water. So if you react it 1-to-1, so you react away all of this with the sodium hydroxide to give you the benzoate ion, so you need that many moles of sodium hydroxide, you're still going to have some that gets produced naturally. And so you need to be above the pKb of this in order to make sure that less than half of this has gone backwards. So if you're going to go through all these calculations, you might as well just put in a really basic solution. And that's what we did, was we just threw a large excess of sodium carbonate into the solution. Because the thing is, we have a whole bunch of hydroxide floating in solution, we're going to drive the reverse reaction. But to say that, well, we need to figure out what pH this occurs at really doesn't make any sense, because what we're trying to do is we're trying to drive a reversible reaction. So the way that you ensure all this is in ionic form is just you run at a pH greater than 11. So you work underneath really, really basic conditions to ensure that this reverse reaction is driven hard and that there's enough base in this solution to remove all the benzoic acid to begin with. So again, yeah, some people really like to emphasize the pKa, pKb for determining what the pH of the solution needs to be in order for you to do the extraction. That's a lot of work, and it presupposes you know how much of this is in your sample, which you don't. So you're better just to run it really high pHs to remove acid impurities and really low pHs to remove basic impurities, and that's a lot easier to work with. You don't have to do any calculations for that. Just run the pH at like 10 or 11 or even 12 if you're feeling really aggressive, and that'll ensure that this reaction sits in the correct direction. Now, the price you pay for doing that, if you run in really basic conditions, is it takes a lot of acid to get you back to a situation where you've got a lot of benzoic acid, but honestly, HCl is cheap. And sodium hydroxide is cheap. question got asked, is the last compound the dibromophenol complex acid or base or neutral? I would argue it's neutral. Phenols can be acidic, but not really acidic. Like it's hard to dry phenol to really like. Well, okay, so phenol is acidic as well, but I would definitely say that that dibromophenol, that benzene ring with an OH and two bromines, that's going to fall on the neutral end of the spectrum. Again, you can kind of argue it's basic or acidic, but I would definitely claim it's a neutral compound, especially under conditions where you're removing the benzoic acid. The benzoic acid is definitely a lot more acidic than a phenol. So if anything is going to protonate first, it's going to be the phenol. So the question is being asked, how would you identify it? So that flow diagram in the pre-lab, it tells you how to identify the acids and bases based on their functional groups. So it's going to tell you what functional group you're looking for in that flow diagram. So it gives you an amine and a carboxylic acid group, and that's what it's defining as acid or basic. The Hoffman product. Give me a minute to open up the notes. I'm trying to remember off the top of my head what a Hoffman elimination is. So I'm not quite sure where you're getting Hoffman product from. That's why I was a little confused. Hoffman elimination is the reaction of an amine where the lightly stable alkene, the Hoffman product, is formed. You shouldn't be on Hoffman eliminations. Those are covered in organic too. Could you give me some context for your question, like where you saw that the Hoffman product is referring to the minor product formed? Because again, this is an organic 2 concept where they do Hoffman elimination with nitrogens. Sorry, responding to other questions as well. Yes. So you do not work with amines. Okay, so I understand your question is no. So Hoffman elimination. Give me a minute. I'm gonna go grab my PowerPoint. Need to go grab a flash drive. I'll be right back. So the Hoffman reaction is an advanced reaction. I would say advanced because this is test 4 in organic 2. So I'll bring up the notes for you to see. But what we do with the Hoffman elimination is we want to eliminate an amine, so we subject it to methyl iodide. And what this does is that the amine here will attack the methyl iodide over and over again until it becomes what's considered an ammonium complex. So it gets this positive charge, and then we can use a reducing agent like silver 1 oxide here to do the elimination. Now, there are a lot of advances to a lot of reasons you would want to run a Hoffman elimination, specifically because it's really easy to detach an amine to some of these groups. The second is that it guarantees, let's see here. It goes against Zaitsev's rule. So when we do a Hoffman elimination, we ensure that basically we're eliminating from the more substituted products. So if we were to just do a straight elimination with this amine, let's say we did a strong base and we were able to pull it off, we'd expect the elimination to be between this amine carbon and this tertiary carbon. With Hoffman elimination, you end up getting an anti-Zaitsev approach. But again, this is why it's kind of an advanced technique. We don't talk about at this level, is that that's amine chemistry. So that's its own separate unit within organic 2. I shouldn't say separate unit. It's its own thing in organic 2 as part of a bigger unit on enols and enolates and phenols. So yeah, Hoffman elimination, definitely organic 2, much further down the road. So the reason why they're bringing up Hoffman elimination is that Zaitsev's rule, which you're learning now, comes into play when we start talking about Hoffman and anti-Zaitsev. So when we go to alkenes, we'll talk about Markovnikov's rule, which says that when you add to a double bond, you always add something that's HX, where X is an anion. And when you add, X always goes onto the more substituted carbon. This has to do with the stability of the carbocation that's generated by this mechanism. Yes. So we'll also start talking about anti-Markovnikov additions because there are times where we don't want to add this to the most stable, most substituted carbon. Zaitsev's rule is kind of the same way, is we don't always want to do elimination from the most substituted carbon, and so this is where we start getting into amine chemistry, and amine chemistry can actually do some really unique things that we can't do with anything else. The two big ones we focus on in organic 2, sort of some Hoffman stuff, but more azide chemistry. So this is an azide. Azides are very good leaving groups, and what you end up with is basically a really good, I don't want to say it, because you break the nitrogen and you end up with a really good carbocation. And it acts like a carbocation, but the cool thing is it doesn't rearrange like a carbocation. So if you want a carbocation on a primary carbon, what you can do is you can take an amine, subject it to nitrous acid, and you'll get the diazonium complex. And this will act like a carbocation, even though R is a primary group. So it comes in really handy at functionalizing primary carbons if you want to do a substitution there. It gets you out of having to do like an SN2 mechanism or something like that. Also, there's a lot of things that will substitute azides that won't substitute alcohols and alkyl halides. Fluorine's a good one. It's really hard to get fluorine onto these compounds, but if you do BF4-, you'll get a terminal halogen. You're also selective. You only get single substitution there. So again, this is more of a preface for Organic 2, but I can see why that video would have covered Zaitsev's rule. If you're looking for exceptions to Zaitsev's, Hoffman elimination is an example of an exception to Zaitsev's rule. But we're not there yet. We're still like, this is just the introduction to reactions. You're welcome. Yes, which one? Page 24. So synthesis with characterization. So we've got the starting compound. And we want to know what are possible major products of this, and what we have is isopropoxide and isopropanol. So we got large bases here. And we're curious what we end up with. So isopropoxide here is going to be a strong base. One initial possibility is just straight elimination of one, and then elimination of the other. And we can definitely have, like, we can do elimination, 1, 2, 3, 4, 5, 6. Principle, we can create this product. 1, 2, 3, 4, 5, 6. Yeah, that works. And so the question is, what did we make with this? Because we've got carbon 13, and it looks like we've only got 4 unique carbons in the molecule with a ratio of 2 to 2 to 1 to 2. I'm going to cheat really quick and look at the solution because I think I know what the answer is. So what we're looking for are carbons that have, where's my chat? We're looking for something that has 4 unique carbons in it. So if I look at this one, I've got 1, 2, 3, 4, 5, 6, 7. So this isn't a possibility. 1, 2, 3, 4, 5, 6, 7. This isn't a possibility. This has a mirror plane, so I have 1, 2, 3, 4 carbons. And if I draw this one, I've got 1, 2, 3, 4 unique carbons. So how about the ratios? Well, I've got a ratio of 2 to 2 to 1 to 2. So I've got 2, 2, 2, 1, 2, 2, 2, 1. So now to distinguish between this one and this one, I need to look up at the, how do you create the cyclic ones? So for that one, you'll get elimination here, and this will attack the carbon and do a substitution. So it's kind of like the synthesis problem actually on the previous page. Actually, it's the same problem as the previous page. It's just there's an extra methyl group on that alcohol. And so with our shifts of 134, 125, 27.9, and 16.2, this 131, 125.7, if you go to tables of normal chemical NMR chemical shifts, what you're going to find is that those shifts of basically 150 to 120, those are alkenes. So we've got 2 alkene carbons, which we'd expect. That's our doublet, our peaks at 1 and 2. And then we've got 2 methyl groups, C27.9, or 2 alkane groups, 27.9 and 16.5. The reason why we don't think this corresponds well is that we'd expect to have 3 chemical shifts here that are consistent with alkanes. So the shifts here should be between 0 and 50. And this one will probably be lower because it's adjacent to an oxygen, but we don't have enough that are in this deep shifted region to really kind of justify that compound. You're welcome. Well, I mean, you struck me as a bit of a sadist, right? Like, why take it out on your cats? Yeah, Squeaky is actually kind of off on her heating pad right now. Anyway, on that note, I'm going to go ahead and cut off the live stream. I do have things I need to take care of today. But anyway, thanks for showing up. I do actually enjoy the questions when they show up. Please don't starve your cats. And I will see y'all Monday.